Hi everyone, good morning. So we are on the subject of image segmentation, and in yesterday's lecture, we saw that there are two ways of approaching segmenting an image. That means you can either follow a discontinuity based approach or follow a region similarity based approach, right? So either you find edges or you find discontinuities, and then identifying those regions, you form a connected component and then consider that to be one segmented region. Or in another example, we saw that due to noise, oftentimes discontinuity based approach may not be the right way to go, because due to noise, that will also be treated as a high frequency information. That means there'll be thousands of edges that will be detected which are not really there, and which is why a similarity based approach or region growing kind of an approach will be more suitable in such a case, right? So the first topic, the first part, which is discontinuity based approach of segmentation, involves edge detection, line detection, or any discontinuity detection, right? So you already are familiar with how to do edge detection using gradients, and this is where you have earlier studied that these are some of the gradient filters, right? Gx, Gy. And what this says is that if you're able to find gradient using these kernels along x direction and along y direction, then the actual magnitude is simply Gx square plus Gy square, right? This is a gradient is essentially a first derivative, right? That means the gradient is a vector which will have a magnitude, and it will also have an angle, which is why you also get angle from gradient, and that is simply tan inverse or arctan of gy upon gx. What does this angle represent? This angle represents the direction of gradient, right? Which will always be perpendicular to the actual direction of edge, right? Because gradient is that direction towards which you found discontinuity. That means if I was looking at a small 3x3 neighborhood, and if I had an edge here, right? So my gradient direction would be pointed in which direction? My gradient would have been found in this direction, right? 45 degrees. This is the direction in which my gradient angle would come out to be. That means the edge is actually in this direction. Okay. So these things you are already familiar with, and you know that these are some gradient operators, Roberts, which is 2 cross 2, Privets, and Sobel operator. Okay, so Sobel operator is very commonly used, very popularly used. However, you know that first derivative is very sensitive to noise, right? That means the moment there'll be a little bit of noise, it is also going to detect those noises. So how do we come up with some mechanism so that the effect of noise is reduced? So there are a couple of results here. So this is an original image, and part B, this is gradient magnitude along x direction. This is gradient magnitude along y direction, and this is simply found by adding up the absolute value of the two gradients. Instead of doing that square of gx plus square of gy square root, this is how it is done. You notice that our objective was to find just edges, but there are a lot of information that have come out. There are no edges as such, right? So one way to address this is how an angle image would look like. One way to address this is to pre-smooth this filter using an averaging filter prior to applying Sobel operator. And you notice that some part of the edges are more emphasized in the detection. However, this is still not good enough, okay? Because essentially what the Sobel operator will find out, it will find out gx, it will find out gy, right? And eventually it will result in a 1 pixel thick structure where only the max, like out of gx and gy, whichever was the maximum value, that pixel it is going to point out. Okay, that is how, if you implement Sobel operator on Matlab, you will see that the output will be a 1 pixel wide edge map, but it is very sensitive to noise. Okay, so this is where there is a need for an edge detector which has a low error rate. And by error rate we mean that it should be able to distinguish, right, whether it's detecting noise or whether it's an actual edge. So we need an edge detector which has a low error rate. It should not be sensitive to noise. It should be able to distinguish that, yeah, this is noise and this is an actual edge in the image. And it should also give us localized edges. By localized edges we mean that, that like second derivative will give you two edges, right? In any practical image, you will notice that the intensity will not just suddenly, like this is the edge of some object, the intensity will not suddenly drop here, right? If you zoom in and if you look at in pixel level, you'll notice that there will be a gradual change in intensity, which is why if you were using these derivatives, you might get multiple edges, because these gradient operators or second derivative, even Laplacian, what it does, it just identifies those regions where there is a discontinuity, right? So it may often give you multiple edges corresponding to those discontinuities. But if I want to localize it and if I want to find what is the center of this object, I had some object, what is the center of that object? So I'm trying to, I need some way to, for you to thin this edge, to do some sort of thinning operation and identify where exactly the center of that edge is located, right? So Sobel is not giving me these things. Okay, Q&A is on if you'd like to ask any questions. Right? So this is what takes us to the next topic of discussion today, and that is Canny edge detection. Okay, Canny is a very important edge detector. Okay, it performs really well. There have been many developments over Canny, means people have tried to improve the performance of Canny or implement it in different ways. But in principle, it is one of the best edge detectors, and which is why it's important that you know how it works. We saw in the earlier example that if you pre-process an image, if you do a sort of a blurring operation on the image before applying Sobel, the effect of noise can be reduced, right? So the first step in Canny edge detection is also to smooth out the image. Okay, so do say a Gaussian blurring, Gaussian averaging, and smooth out the image. This is step number one. Step number two is just use Sobel operators and find the gradient. So it's not written here, but you use Sobel operators. Okay. And what will Sobel operator give you? Sobel operator will give you gx, gy. As a result, it will give you square root of gx plus square root of gy. This is the magnitude, and it will also give you the angle, right? And you know from the angle, this is the angle corresponding to the direction of the gradient, perpendicular to which would be the direction of the edge. That means at every pixel, you have the idea of in which direction the edge should be, the edge would be. Okay, the pixel which is lying on the edge, in which direction is this pixel edge supposed to be, you will get that idea from this Sobel output, from the magnitude and from the gradient. Second step is done. Next step is called non-maximum separation or non-maxima separation. Okay, what we are trying to do here is to fix that problem, which I said that there may be multiple edges, right, while trying to find any in any real photograph, in any real digital image. You will notice that transition of at the edge of any object will not rapidly, it will not suddenly change, right? It will gradually change in any real photograph. which is why it is important that if I want to localize the edge, that means I want to find what exactly is the center, what exactly is how I can represent this edge as a 1 pixel thick line, just 1 pixel, not multiple pixels or not multiple edges. I just want 1 pixel. How I can do this? So this is what is non-maximum suppression. So what it does is it looks along the edges. It looks at small neighborhoods along the edges, and if across the edge, not along the edge, but if across the edge, a particular gradient value is the maximum, the magnitude value is maximum, it will retain those values and it will drop all other values. It will drop the other pixels which had gradient non-zero, right? But if it is not a maxima, if it is not a maxima in terms of magnitude, it will drop those values. And with what it wants to compare? It wants to compare only with those pixels which were in the same direction, which were along the same edge. So let me show you an example. 1 second. Okay, so this is a test image that I'm considering. So let us look at just one location of this building. Okay, so let me zoom in. This is the image region viewer of Matlab. Okay, so I'm zooming in. Because this is a real image, a practical real world image, which is why your edges will not be 1 pixel thick. You will have a broad edge. But if I now wanted to localize and say, you know what, give me one location, give me one single location, which I should consider as the location of the edge. Help me localize this edge. So what does it mean? Okay. So say I'm looking at just this small neighborhood, right? And if I have, for each of these pixels, I have the value of gx, means I have the magnitude, and I also have the angle of the gradient with me. So because I can see that the edge is in this direction, right? That means when I'm saying I'm doing non-maxima, what do I want to compare it with? I want to compare the value of gradient magnitude of this pixel with this and this, because this is the direction of my edge. Okay, so all I need to find is the gradient magnitude at this location, is it the local maxima of these three? If it is, then I'm going to keep this pixel, I'm going to retain this value as the edge value, and I will drop these other two. If it is not, then I'm going to look in the other neighborhood. Okay, so note that when I'm trying to find maxima, and what is this term? That whatever is not a maxima or not a maximum, you drop those pixels. Okay, and how do I select this maxima, or how do I evaluate? I have the value of the magnitude as well as the gradient. So in any neighborhood, I am interested in finding which of these pixels should correspond to the maximum gradient magnitude, right? So I'm going to compare all those pixels which had gradient in the same direction, or rather edge in the same direction. Gradient would have come in this direction in this case. Direction of edge is this. So I'm interested in doing maximization in that sense. Okay? So if I was not looking here, if say I was in some other part of the edge, say I'm here, right? So I know already that the edge would have, direction of edge is in this direction. That means if I'm considering any small neighborhood, I'm interested, if I'm looking at this pixel, I'm interested in the magnitude of this pixel and in the magnitude of this pixel, because that is what corresponds to the same gradient angle. So here, of course, when you find gradient angles, you have to kind of reduce them into, these are the only angles that you have, right? Only increments of 45 degrees each. You don't have any other option. How do we decide the direction of the edge? You already have angle, right? You already have angle of the gradient, which is tan inverse gy by gx. For every pixel, for every single x comma y, you have the value of angle. This is the angle of gradient. You add 90 degrees to it. That is the direction. So this is, say this is the direction of your gradient. Add 90 degrees to it. This is the direction of your edge. So we've done smoothing. We've found gradients. We have also done suppression. That means we are only retaining local maxima, those values of gradient magnitude, which is maximum along a particular direction of edge. Only those I'm keeping. I'm losing all other. And it goes even further. Canny Edge Detector even goes further and says, you know what? Let us do a further double thresholding. And by double thresholding, we mean hysteresis thresholding. So as the name suggests, it will have two thresholds. And now, even from those, after doing non-maxima suppression, you have identified the localized, local maxima of each edge. Canny Edge Detector is still ready to drop some of these edges if they are not strong enough, okay, or if they are not really connected to a strong edge. So this is what is called double thresholding, where what you will look at is, now you will look at edge responses, and you will set two thresholds. So say if I'm looking at just a profile in one direction right now, not in two directions. So if I had a profile like this, okay, what is this? This is the edge response. Say this is magnitude gx along any one direction right now. Okay, so if I'm looking at such a profile, and if I found that, okay, see, in this region the response is pretty high, right? This is a magnitude, means there must have been an edge. In this region also the response is high, right, but not as high. But in this region, let me actually have some regions which has very poor response. Okay, so of course, so this region is corresponding to large magnitude, large response in edge. This region also has a large response in edge, but it is not as high, right? But there are certain regions which have a very poor edge response. So double thresholding means that I will set one threshold for the gradient response, say higher threshold. Everything above this threshold is definitely going in. All the edges which have a gradient response, gradient magnitude above this threshold are definitely in. I will also set a second threshold, a lower threshold. Everything below this threshold is definitely out. Means the edge response was not strong enough. It probably was, some discontinuity, or some maybe some noise, or some patterns in the image which really do not contribute to a strong edge. Those must be those regions. So I'm saying anything below my second threshold, my lower threshold, I'm definitely dropping. Okay, but what to do between these two thresholds? If for those pixels where my edge response is greater than lower threshold but lower than the higher threshold, I will just look at whether that pixel is actually connected to another strong edge. Meaning anything above this upper threshold, I'm considering to be a strong edge. Okay, it's a strong edge location. Anything below my lower threshold is a weak edge. I'm going to drop it. I'm not interested in it. But anything between these two thresholds, I'll look at whether those pixels are actually connected to a strong edge. If they are connected to a strong edge, I'm going to consider that, okay, fine, nothing to worry about. Probably it is a part of the same object, right? So in some portion, maybe illumination was not proper, which is why those edges did not come out very well. They have given a weak response, but they are probably connected to if we just traverse the pixel location, if we find that they are connected to a strong edge, means they are probably a part of the same object, right? Which did not come out very well in the object perhaps. So we are going to take them. We are going to consider them. Okay, this is what is called double thresholding. Even after localization, pixels that got through and found that they are local maxima, we are doing a third level of testing on them and classifying them as strong edge or weak edges, even if their response was somewhere between these two thresholds. If they are physically connected to another strong edge, then we consider it to be a strong edge and keep it. If not, we can drop it, which means that the Canny edge detector actually operates on these threshold values, and you can tune these threshold values yourself to get different types of responses. Okay, so if I suppose had kept this lower threshold very low, if I had kept this very low, right, in that case, almost nothing would have been rejected, right? Almost nothing. If I had kept the upper threshold too low, then almost everything would have been considered as a strong edge. Even noise, all the random things that would have been there in the image, which are not edges, everything would have been considered as an edge, because the upper threshold would be too low, right? Which is why it is important that depending on your application, depending on on your use, you choose these threshold values appropriately, and for different values you will get different types of responses. Okay, so this is my input image. This is my Sobel output. This is the output that I get for Sobel filter. Okay, Sobel gradient, edge detection using Sobel. And you notice that if I zoom in a little bit, you notice that there are a lot of broken edges, right? If I now look at this result, this is the Canny output. If you zoom in a little bit, you notice that there are a lot of connected components, right? How did this happen? This happened because Canny was doing multiple things. It took Sobel input, fine. Then it also decided where the local maxima of edge along a particular edge should be. Then it further went on and said, okay, if I'm going to keep only the strong edges and I'm going to lose all the weak edges, which is why the edge detection result that you get from Canny is much better. This is how gradient magnitude looks like. Okay, gx plus gy, the square root of the magnitudes, this is how that looks like. And if you look at just the magnitude, I'm going to focus on the same region in both the images. So I'm focusing on this floor of this library, this clock tower, right? So you notice how there are multiple values in this gradient, and the purpose of doing that non-maxima suppression was actually to thin this region, to do a sort of thinning operation and get just 1 pixel wide representation of a maximum gradient along this direction. This is how the gradient magnitude looks like. This is how my input image was, the same region in my input image. How do I identify? If I look at the pixel location, so let me go somewhere here, say 1652, 912, 911, something like that, like this location. I'm going to find this same location for my Canny. Okay, I was on the wrong floor of the clock tower. Yeah, somewhere around this. Right, so let me try and place it side by side. This is the location. Let me zoom in one more. Right, so this is what my location was, say 1600 cross 920, 1652 cross 920, this pixel right now where my cursor is, and the corresponding 1650 comma 920. Right? So actually 1652 it was not a local maxima along this direction in terms of gradient magnitude, and which is why Canny actually dropped it, and the edge was actually found at 1650. And if you compare this performance with Sobel, do you also notice this is a Sobel output? Do you notice how Sobel has all these broken edges like randomly lying around? Right? Because Sobel has not done that double thresholding. It has not tried to get rid of weak edges. Another important point to note here is that, say, this is a Sobel response, right? In the Sobel response, do you see a white dot over here? There was some noise in the original signal. This black dot in the original signal, right? In the original image, and some bird. Canny actually got rid of this. Canny did not give me this value. Where is Canny output? Yeah. Canny response did not have anything over there. It did detect the bird. No, this is Canny. So it did detect the bird, but it did not give me that noise. Whereas Sobel actually fell for that noise. Sobel did not get rid of that noise. So if you look at the images overall, this is the original image. This is the Sobel output. And this is the Canny output. And you notice that the Canny output is significantly better than the Sobel output, and the flexibility of choosing thresholds, the two thresholds that you can adjust, gives you an added advantage. And what are the steps that you follow in Canny? Let's recapitulate. The first step you do is smoothing. The next step is finding gradients, doing simple Sobel. So actually Canny takes the Sobel output as its input. Then it does non-maxima separation, chooses only local maxima that should be treated as edges. It's trying to localize the location of the edge. And then it does double thresholding, followed by tracking. If retain strong edges, lose weak edges, but among the weak edges also you can take and keep those edges which are connected physically to a strong edge, because they might, there's a large chance that they might be a part of the same object. They might be the edge of the same object if it is physically connected to a strong edge. Okay, which is why Canny edge detector is one of the most popular edge detectors. There have been many implementations and improvements over this Canny edge detector as well, which you are free to check out. There's a question somewhere. How are the empty spaces in the edges filled by Canny? So empty spaces are not being filled. See, what exactly is happening here is, it is not filling empty spaces, okay? What it did was, let me go back to my gradient magnitude. So this is Sobel gradient magnitude, right? So if I look at this small neighborhood, what is happening here? You notice that the gradient is giving you some response. So why is this appearing white? Because the value, the gradient magnitude in this region has come out to be large in value, right? Which is why this is appearing as bright, because the corresponding magnitude has been mapped to an intensity level just for displaying the magnitude, right? Displaying the image. So what Canny is trying to do is, this is not 1 pixel wide. This has 1, 2, 3, probably, yeah, this is 3 pixel wide, right? I want to localize the edge. That means I want that you give me one location where I can say that, yeah, this is where the edge lies. Give me one such location, 1 pixel wide. So how to find that? That is what Canny does by non-maxima non-maximum suppression is a way of doing thinning in this case, right? Thinning to localize edges. How are TH and TL selected? Yes, it's a manual selection and you can change it in, please try this out in Matlab. You can choose different values of thresholds and you'll be able to see how changing lower threshold, upper threshold can change the visualization. Like if you change the threshold too much, you will notice that for some images, like Canny will start behaving just like Sobel. Because of smoothing, that bird is not detected by Canny. No, so Canny actually did detect the bird. Where's the bird? The bird is in the very corner. Where is it? Yeah, this is the bird, right? This is the noise, because it probably is also a bird, but it is too far away, so it is just a small discontinuity. This has a bigger figure, right? It has a larger area. So if you look at the Canny response, Canny actually gave us output. Right? See, Canny actually gave us output for the bird, but it did not consider that noise. Yeah, this is how Sobel's response was. Pretty broken, right? So please try it out on Matlab, which is a step that suppressed that noise. It is that double thresholding which suppressed that noise. Yeah, if you change the threshold, it can detect the small bird also. In fact, if you change the threshold too much, it will actually detect all the, like, it will detect all the blobs which are actually there in the background, because the actual gradient magnitude image, you notice all this information in the background. This is the noise which is there in the image, which is in the sky. It's an evening sky, right? And so all this part, this will also get detected in Canny if you change the threshold. Okay. Any questions? Okay, so Canny edge detector is a very important topic, okay, when we speak in terms of edge detection, which is why Sobel, of course, performs well, but we can improve Sobel and we can get rid of the problem of noise and edges which are not really useful. We can get rid of all that using Canny. Why the overall image in magnitude gradient looks bright? Is it because of noise content in the image? It is looking bright because it is actually adding two separate gradient values. It is doing gx square plus gy square, its under root. Probably in Matlab, it is just doing mod of gx plus mod of gy, right? So you are adding two gradients. That is why it is appearing brighter. Like the edges are appearing super bright. How is it getting local maxima? Because many neighbors have the same intensity. No. So it is finding. Okay, you are saying that even if the magnitude was the same, how does it find local maxima? The magnitude at every location is not same. It may look the same in the image because, of course, when I'm representing a gradient magnitude in the form of an image, I'm mapping these values on a scale of 0 to 255, right? So you may see like all of them are appearing to be 255, which does not mean that all of them have the same gradient magnitude. Okay, because the image is actually clipping 0 and the 255. Okay, so some more results of Canny. This is how Sobel works, and sorry, this is how log works. And so log is another type of operator. Okay, please go through it. That is Laplacian of, it's actually Laplacian. I don't know why I say Laplacian. LOG, Laplacian of Gaussian. LOG. Okay, so it's a, if you have a, it's a second derivative of Gaussian. So please read about this operator also. This is also an edge detector operator. On the subject of discontinuity based segmentation, we have discussed edge detection, and among edge detection, you know many such tools. So you know gradient, Sobel. You'll also study LOG, and you have also studied Canny. Second part is to detect a line. Can you tell me what is the difference between an edge and a line? This is the edge, and this is the line. So a line is essentially going to have, you can say it has a gradient in this direction as well and in this direction as well. That is what is a line. An edge would have a gradient only in one direction. So very qualitatively looking, the terms are very similar, but this is what is the difference between an edge and a line, and which is why edge detection is using all these tools and line detection. So what are we assuming? That when I'm doing line detection, I have already got my edges, right? I have detected where these edges are, and these edges have been detected in the form of a, say, a single pixel thick structure, right? So I have already done my edge detection, and after doing edge detection, I have got all the possible edges in my image, and now in those edge pixels, I want to identify whether there are straight lines present or not. A line will be of the form y equal to mx plus c. So if I'm saying detect line from the edges, I'm saying detect those set of edges which are collinear, edge points which are collinear. Okay, I could have used half transform to detect circles as well. So it is not that you can only detect line. Okay, and what does, so the premise has to be very clear here. We have already done edge detection using perhaps the best possible edge detector available to us, and eventually what we have is a edge map where something like what I just showed you earlier, right? The Canny output. It is a binary output which has 1 pixel thick locations where there are edges localized. Now our task is to detect where lines occur or straight lines occur in those edges, right? So the input to our half transform is actually just the output of the edge detector operator. Okay? And how does half transform really work? Half transform says that if I have a straight line of the form y equal to mx plus c, I'm going to map this into a parameter space, right? And of course, the parameters are m and c, but then we saw that the limitation of using m and c as the parameter space is that if m becomes, for vertical lines, the slope becomes infinite. So it goes beyond our parameter space. You cannot place it there, right? Which is why we said that it's a better way, instead of in terms of slope and y-intercept, it is better to parameterize this in terms of radial distance and angle, in the sense that if I have a axis like this is my x and y, right? And I have a straight line which normally would have been represented in the form of y equal to mx plus c. If I now say that if the radial distance, if the perpendicular normal distance of this line from the origin is rho, and the angle it makes from the x-axis is theta, that means this line can now be parameterized in terms of rho theta axis, right?